Alright, welcome back to my attempt at making some accessible virtual learning for you. Alright, so this unit is going to be about preparing a budget, and it's going to be about basic bills and that kind of stuff. So, brand new unit, I'm designing it specifically for virtual access and virtual learning. Lots of videos, lots of this beautiful face, right? Bringing it to you, the education you deserve, alright? So, put your name in here. Put your name in here. Watch the little video. Take it from the top. That's my little pep talk. And all right, back to it. Learning targets. Learning targets we have here. Let's see. First learning target. Remember these lessons here. These lessons are multiple day lessons. They would take us normally 3 days to complete these lessons. So I want you to keep in mind that this whole section 1 here, utility expenses, this is what you're looking at, this Google form you're looking at right now is section 1, utility expenses of the unit, personal budgeting and expenses. Each section is going to be about 2 or 3 days of class time, maybe up to a week of class time, depending on how things go, and attendance and all. So keep in mind, this might take you like a whole week to get through. If it takes you, a half hour a day for a week, that's about what's expected, okay? So take heart. So again, the unit is personal budgeting expenses. What you're looking at right now is section 1, utility expenses. In the next Google form, section 2, we're going to look at electronic utilities. In section 3, we're going to be charting a budget. And then in section 4, cash flow and budgeting. That's going to be the last section. We're going to do a lot more personal budgeting stuff. So again, put your name in there, watch the video, and learning targets. Learning targets for this section. Learning targets for this section here is, I can compute the cost of electric, gas, oil, and water for the home, and I can compute the cost of using specific appliances for specific lengths of time. And the third learning target is I can compute the time it takes an energy-saving appliance to pay for itself. All right, here's the vocabulary. Well, actually, you know what? I already went over all this vocabulary in this video right here, my vocab video. So I'm going to skip that. This is a picture of that natural gas utility meter I promised you in this little video right here. There's the Common Core standards. That's really for the teachers that are there. Maybe I should put this at the bottom, the standards. You probably don't need those, but, I put them up here. I put them up there so you can look at them if you want to. Okay, learning targets. Learning target, well, I kind of tricked you, right? The learning target is back over here. You got to go back up, find learning target. Remember those. You can compute the cost of electric, gas, and water for the home, and compute the cost of using specific appliances, and compute the time it takes for an energy-saving appliance to pay for itself. Okay, so hopefully you can copy and paste, of course. I know that's what most of you are going to do, but I do want you to actually think and read those learning targets. Those are important. Okay, so example 1. Example 1 here is, how can you determine how much water you used from a previous reading to the present reading? So remember that vocab, previous reading and present reading. All right. Let me see if my technology is working. All right. Yes, good. All right. That's a vocab word right there. And that's a vocab word. Okay, so the previous reading was a reading of a meter previously, and the present reading is currently what the meter reads. I'm going to show you how to read a meter in a next example, all right? But example 1, Tom's October water bill listed 2 meter readings. The previous reading was 3,228 CCF. Remember, CCF is a cubic foot, right? A cubic foot of volume. In this case, it's a cubic foot of water. And the present reading is 3,141 CCF. How much water did Tom's household use during the billing period? So, how can we determine how much water we use from a previous reading to a present reading? Well, if the previous reading said it was at, the previous reading said it was at 3,128, and the present reading says it's at 3,141. So what we have to do is subtract, right? We have to take the difference to find out what is 3,141 minus 3,128. So here's the solution. The solution in all these examples I give you has the problem, and then the solution. The solution, how do you figure this out? You take the present reading, right? And then you subtract the previous reading, which gives you 13. This number minus this number is 13. So guess what? Tom's household here used 13 cubic feet of water during the billing period. That seems not very much. I don't know if that's quite realistic. All right, we'll move on though. I give you a similar, less than realistic situation over here, right? So here's Corey's water bill. Same exact problem. So I'm trying to give you one problem after the example. It's just like the first. Corey's water bill listed two meter readings, just like Tom's. The previous reading was 8,508 cubic feet of water, and his present reading is 8,535 ccf of water during a summer month. How much water did Corey's household use during the billing period? All right, so, well, I want you to look at that previous problem to figure out how to solve this. So previously, we took the present, right? Took the present, and we subtracted the previous to find the difference. So that's what we're going to do here. We're going to find the present is 8,535, and we're going to subtract 8,508, and we're going to use our calculators here. And oh, you know what? No. What did Mr. Salt do? Because he's all distracted with trying to teach this stuff here. Mr. Salt, you want the bigger number first, right? So, well, actually, the calculation I just wrote, that would have worked for us. This would have given us a negative number, which we would have to reinterpret. So it's 8,508. That's the previous. And then the present is 8,535. And I want to subtract the present minus the previous to give me a difference, and I think that's going to be 27. Alexa, what's 8,535 minus 8,508?
8,535 minus 8,508 is 27.
There we go. You'd use your calculator for that, so that's what we got. 27 ccf. CCF. Whoops. Oh, sorry. I'm playing with my technology here, and I pressed a button I didn't realize I had. All right, so now I'm going to get rid of all this, and we're going to move. Oh, and then I got to get rid of the annotator. Okay. Sorry. I'm still playing with this virtual technology here. And how do I make the virtual technology go back away? Okay, there we go. Forgot about how to do that. Okay. This is one of those ones that I know you all hate. Okay, this is that express algebraically, and I'm just stuck on this because this is this higher level mathematics that I want you to get. So anyway, Ariona used X ccf of water during the summer month. All right, so we're going to express how much she used is going to be X. Express the number of cubic feet of water she used algebraically, where the previous reading is represented by V and the present reading is represented by S. All right, so remember what we did. We took the present reading and we subtracted the previous reading to find the difference, right? So if the present reading is S, we're going to subtract the previous reading. So S minus V is going to give us X, right? S minus V will give us X. That's how we solve this one. That's expressed algebraically. No numbers, nothing to compute. That's just what it is, all right? So that's how to solve that one. All right, so here's my I promised you we'll go over one where how to read a utility meter, okay? How to read a utility meter. So Janet works for a utility company and is reading the Savitz household's electric meter. What is the reading? All right, what is the reading? So here's the solution. Notice where the arrows point on each dial. The correct reading is the lower of the two numbers closest to the arrow. So it's always the lower of the two numbers closest to the arrow, with one exception. If the arrow points between 0 and 9, this is read as 9. All right? So it's always the lower unless it's between 0 and 9. So we would look at this one, and we would read this one as 0. So it's like a clock. This one's actually going counterclockwise. Once it starts at 0, goes to 1. So this dial is spinning this way, which is why we have to say we're going to read this as 0. It's not yet at the 1. All right? This one we have 0 and 9, which means this one must be spinning this way. This one must be spinning this way because we have 0 here and 9 there. Notice how that's different. So this one's spinning the other way, so we're going to read this as a 9 because that's one of our exceptions. Read between 0 and 9. This one's spinning this way. It's not quite at the 0, so we read this number as a 9. So this one we're going to read as a 0. This one we're going to read as a 9. This one, it's between the 5 and the 6. It's spinning this way. Right? It's going from 5 to 6. It's not quite at the 6, so we read this as a 5. This one here is going from 5 to 6, so this one is spinning this way. That dial's going that way, so we read this as a 5. Read this as a 5. Between take the lower of the two numbers, and this one I can see it goes from 1 to 2, so I can tell that this dial is moving counterclockwise. It's not yet the 2, so I read this as a 1. So if I was to read the numbers on this dial, I would get 0, 9, 5, 5, 1. That is the reading on this dial. 9,551 kilowatts of electricity in this case. And actually some of this is old stuff, like, right? I mean, I still have these dials on all of my stuff, except I think maybe my natural gas is now an electronic meter. I think they replaced that last year. But a lot of these are now going digital, and you'll be able to read these a lot easier going into the future when all these become digital, right? It'll just be a digital readout. None of this funny business of clock dials going every which way. But until all that happens, we're stuck with the dials for those of us who still have them, right? So what is the CCF reading indicated on this dial? So maybe you want to pause the video, give this a shot right now. Give this a shot, unpause the video, and come back, see if you got the same answer. All right, so you've unpaused the video and you're back, right? You took a shot, right? Always take your shot. Always take your shot. All right, so I can see this one is moving this way. This goes from 3 to 4. I see it's not yet at the 4, so I say that's a 3, right? Take the lower of the two numbers. I can see this one is moving in this direction. It's not yet at the 4, so I read that as a 3. I'm looking this between the 5 and the 6. I can see it's going this way. It's not quite yet at the 6, so I read that as a 5. And here I can see this one here. It's going, and remember this is my exception. Oops, sorry, that's my exception here. It's going this way. It's not quite at the 0. I read this as a 9. So 3, 3, 5, 9. That's CCF. Always put your units on here, CCF. All right. So that is that. That is that. Let's go to the next one. All right, here's a picture of an electric mixer. For those of you who don't know what an electric mixer looks like, because I'm going to use an example of an electric mixer. I want to make sure we all know what we're talking about here. So a certain electric mixer requires 125 watts. How much would it cost to run the mixer for a total of 90 minutes at a cost of 10 cents per kilowatt hour? All right, so here's how you would solve this kind of thing. And again, the point of this example 3, is how do you calculate how much it costs to run an electric appliance? Remember that second learning target? Look at that. You're already on the second learning target. All right, so to calculate the solution here is to calculate the operating cost of an electrical appliance by checking its wattage and the time it is being used. So first, we need to convert this 90 minutes into hours. We need to convert this 90 minutes into hours. So this 90 minutes has to be converted into hours. And how many minutes are there in an hour? Well, there's 60. There's 60 minutes in an hour. So 90 minutes divided by 60 gives us 1.5 hours. We know this electric mixer is going to be used for 1.5 hours. Yeah, that's a lot of mixing. All right. The number of watt hours is the product of the watts and the number of hours the appliance is in use. So we know that it takes 125 watts of electricity. There's 125 watts of electricity. We know that it's 1.5 hours. There's our 1.5 hours. Well, 125 times 1.5 is 187.5 watt hours. That was one of our vocab terms. Okay, the electric usage is billed by the kilowatt hour. Now that's another vocab term. Kilowatt. That's 1,000 watt hours. A kilowatt hour, kilo, means 1,000 kilowatt hours. So to express 187.5 watt hours as kilowatt hours, we need to divide by 1,000, right? So we're going to take here's our 187.5 watt hours. Sorry about that. I got a little clock in here that will ding every 15 minutes. Apologize for that. 187.5 divided by 1,000. That gives me 0.1875 kilowatt hours. And this allows me to be able to figure out how much I'm going to get charged, because I get charged by the kilowatt hour, right? Kilowatt hour costs about 10 cents. So multiply our kilowatt hours that we found here by 10 cents. There's our 0.1875 that we got from over here, times the 10 cents, and we find that it's about 1.9 cents to run this electric mixer for an hour and a half. All right, that's not too expensive, right? All right, we're going to get rid of this. Moving down. All right, very similar situation. What we're dealing with here. You buy a refrigerator that requires 180 watts. Now, actually, your refrigerator takes a whole lot more watts than this. Your refrigerator might be, anywhere from 400 to 800 watts. But this is going to be an average watts per hour in a 24-hour period. I had to play around a little bit with the math here to get the similar situation because this runs all day. This runs all day. So that's what I want you to think about. The refrigerator will turn on for a total of 1,440 minutes each day. And if your utility company is charging 10 cents per kilowatt hour, how much will it cost you to run a refrigerator per day? I'd like you to pause the video here and see if you can tackle this on your lonesome and then come back, okay? So pause now, give this a shot, and then turn the video back on, and you'll see me do it. All right, great. You paused it. You figured it out. All right, so first our step. Remember from our previous situation, we got to convert it into minutes into hours, okay? I'm going to be tempted to keep flipping back and forth, but I don't want to do that too much. So I'm going to go over to use the margins on my paper over here, and I need to do 1,440 divided by 60, right? Because there are 60 minutes in 1 hour. And when I calculate the minutes divided by how many minutes are in an hour, I'll get how many hours that is. And I throw that in my calculator, and I find that's 24. And I set that up because I wanted it to be 24. I want this refrigerator to essentially be running on an average of 180 watts for over a 24-hour period. All right, so it's running for 24 hours a day, right? All right, so it's running 24 hours per day, and it's 180 watts. So 180 watts times 24 hours. Alexa, what's 180 times 24?
180 times 24 is 4,320.
4,320. All right. 4,320. And what did we just find? We found this is the kilowatts it takes. This is how many hours it's running. So this is how many watts it's running. This is how many hours it's running. So these are watt hours. 4,320 watt hours. Okay? 4,320 watt hours in a 24-hour period. I then need to do, let's see, I take the watt hours like I found over here. Remember? And then we're going to do what to it? We're going to take the watt hours. We're going to divide it by 1,000. So 4,320 divided by 1,000. Alexa, what's 4,320 divided by 1,000?
4,320 divided by 1,000 is 4.32.
4.32. So what did we just found? We just found the kilowatt hours, right? Just like we took the watt hours divided by 1,000 to find the kilowatt hours over here, we're doing this exact same thing. Here's the watt hours. Dividing by 1,000 gives us the kilowatt hours. So kilowatt hours, all right? And I forget, I think that this W's got to be capitalized, actually. Okay, anyway. And then, so we know that we're getting charged, what was I say, 10 cents per kilowatt hour. So it costs us 10 cents per kilowatt hour. So 4.32 kilowatts per day times 10 cents, right? 10 cents. Alexa, what's 4.32 times 0.1?
4.32 times 0.1 is 0.432.
0.432. So that's kind of our answer over here. That's kind of our answer. Per day, how much does it cost per day per 24-hour period? It's going to cost us about 43 cents. About 43 cents, approximately. 43, we could say 43.2 cents. If we were going to calculate it for some longer period of time, we might do that, but we might just say 40.43 cents per day. All right, so that's this one. You can pause here if you need this work or whatnot. but I'm going to make it go away. Well, I'm going to make it disappear there, and so I can scroll down. My next question I'm going to make a little harder. I'm going to ask you how much will it cost to run your refrigerator per year? Well, you're just going to take how many days are in a year? I'll have you search that on yourself. Okay. Let's see. Appliance uses W watts. So again, this is that express algebraically thing. I know you all hate this, but I want you. This is like expressing things algebraically is one of the key of kind of like making your thinking explicit in math, because this way it doesn't matter what the numbers are, you know where to put the numbers. But now we're just using letters instead of numbers, or variables instead of numbers. All right, so stick with me here, stick with me. All right, appliance uses W watts. So the appliance uses W watts. We're going to run it for M minutes, and the cost per kilowatt hour is C. All right, express the cost of running the appliance for M minutes algebraically. All right, well, our first thing, remember our first step was to figure out, we needed to convert the minutes into hours. So our first step is going to take the minutes, whatever that are, and we're going to divide by 60, right? Because this will give us an hours, right? And then we're going to this hours, we're going to multiply it by how many watts the thing generates. So we're going to multiply it by how many watts the thing generates. And then what are we going to do? Well, then we're going to what? We're going to divide it by 1,000, right? Take this and divide it by 1,000, right? Which will give us the kilowatt hours. The kilowatt hours. And once we get the kilowatt hours, we're going to multiply it by how much those kilowatt hours cost each. All right, so we're going to multiply all that by C. If I was to write this all in one line, you know, I could use other ways of doing this, but I probably should have written it out in one line because you have to write it all out in one line. All right, let me try this one more time. No, that's not what I wanted. I pressed the button I didn't want. All right, W of M divided by 60 divided by 1,000 times C. All right, that's kind of the same idea. I'm relying on some PEMDAS rules here, right? I'm relying on some PEMDAS rules. I don't need all of the parentheses I used for this over here because I'm relying on those PEMDAS rules that are kind of where things are implied. But I think that works, right? So that's not 160. That's divided by. Sorry, that looks like a. I gotta stop pressing that button. Sorry, new technology. I'm writing on a little electronic tablet over here. All right. So I'm going to get rid of this. Pause if you need it. I'm going to scroll down. Example 4. Example 4, how do I calculate the monthly utility payment for a utility? So how do I calculate the average monthly payment for a utility? Okay, so depending on your climate, your utility usage can vary according to the seasons, right? Electric bills can be higher in the summer due to air conditioning, right? And in the summer, we're using a lot of air conditioning. And in the winter, we're going to use a lot more gas and oil. So gas and oil usage can be higher in the winter due to heating needs. For this reason, some utility companies offer balanced billing. This evens out the monthly cost of utilities to make the homeowner's payments more predictable. Last year, the Ross family spent $3,336 for electricity, and they are opting to use balanced billing for next year. What will their monthly payment be? So the advantage of this balanced billing thing is they kind of average all your monthly payments out. So that way you're not getting killed by an electric bill in the summer or by a natural gas bill in the winter. You just kind of pay the same amount every month, and it just kind of makes life and budgeting easier. So here's a solution. Here's how you figure this out. Balanced billing uses the previous year to determine monthly payments for the upcoming year. So you divide your average cost by 12 to get a monthly average cost. So your annual utility cost goes here. You divide by 12 months. So if your yearly bill last year was $3,336, you divide that by 12, and you found that the average utility bill was $278 per month. $278 per month, and that means under balanced billing the next year, you'll pay the Ross family will pay $278 per month under a balanced billing program. I'm getting rid of that. I'm scrolling down. All right, here we have a situation with Renice. Renice spent $2,782 for electricity last year. What is her monthly average charge for electricity based on last month's data? I want you to pause the video, and I really hope that this is an easy piece of cake for you, okay? Go for it. Pause it. All right, you're back. You unpaused it. Good on you for trying this on your own. This is pretty simple, right? So this was what she called this. This. Okay. And let's see if I can go back. No, I can't. Okay. 2. Renee spent $2,782 last year for electricity. She wants what is her monthly average charge? So this is that balanced billing thing. That was what she spent last year. We're going to divide that by 12 because there are 12 months every year. And we need to do some computation here. Alexa, what's 2,782 divided by 12?
2,782 divided by 12 is 231.8233.
231.833. And in financial situations, we're just going to ignore this, right? We're going to ignore this right here, right? We're going to get rid of all that because this is going to be a dollar amount. We can't pay fractions of a penny. So she's going to pay about this, and maybe her last bill will be 84 cents instead, or 85 cents to make up the difference, right? Okay, pretty easy stuff, pretty easy stuff. Now we got this algebraic stuff coming up again. Let me move this. Oh, let me change this over. Haha. All right. Here we go. Let me dump that from the previous lesson. There we go. Okay. 2 years ago, the Kelly family used Y dollars of electricity. Last year, they used balanced billing. During last year, they used X dollars of electricity, and their balanced billing payments were not enough to pay for their electric usage. The Kelly family, they had to pay the difference at the end of the year. Express algebraically the amount they owed the utility company. Okay, so it goes like this. This is that skill of algebraic, expressing things algebraically that I want you to get. Unfortunately, you probably all see that I accidentally left you the correct answer right here on this form. That's okay. I want you to, so last year they used X dollars electricity, right? There's X. And 2 years ago, they used Y dollars electricity. And somehow X was more than Y, right? Because the payments based on the Y data, the payments based on the data from last year, was not enough to pay for the electric usage. They used more. X is greater than Y. If they paid the same as they did this year, Y, and that's not enough, that means that whatever they owe, X must be more than Y, right? Because X must be higher because they didn't have enough to pay for electric usage. So to figure out what's the difference at the end of the year, what's the excess they had to pay, we're going to have to do X minus Y, right? X is the bigger number. That's what they used for electricity this year, or during last year. And 2 years ago is the Y, right? 2 years ago was Y, and X is last year. All right, so X minus Y is going to be how we express this. X minus Y is the difference between last year and 2 years ago, which is what they still owe the electric company. All right? I know we don't like those, but I want you to really I want you to think mathematically, right? I don't want you to be too impressed by numbers. I want you to be impressed by the reasoning, the problem-solving skills, the figuring out the mathematical relationships between numbers. The numbers themselves are incidental and vary. I want you to think about, what the skill is that you're learning. Okay, example 5. I think this is our last example. How do I calculate the expected return on investment for an energy-saving appliance? All right, expected return on investment for an energy-saving. How will I know when the savings of an electric energy-saving appliance will have justified the cost-expense of purchase? All right, so here we go. Example 5. Energy savings often pay for themselves. This means that the savings in energy usage can equal or offset the cost of the item after a certain number of years. The Thompsons' old water heater cost them $455 per year to run. The new one they purchased for $1,240 will save them 31% annually in energy costs to run it. In how many years will it pay for itself? Okay, here's the solution. How will we figure out how many years will it pay for itself? That's what we're trying to figure out right here. Well, the first step is to compute the savings per year by finding out whatever 31% of 455 is. All right, so here's how do we find of. When you see of in a mathematical word problem, I want you to think multiplication. All right, 31% of. Well, you also know that you're going to take this percentage and you're convert it to a decimal by now. We're doing a lot of that this year. So 31% can express as a decimal out of 1 is 0.31, right? So 455 times 0.31 is 441.05, right? $441.05. That's the savings per year. All right, this is the saving. This is the amount of money saved per year. Now we're going to figure out when will this thing pay for itself, right? My savings per year, by getting this new appliance, I'm saving $141.05 each year. And then figure out how many years will it take for this savings to basically pay for the justify the expense of the new appliance. Here's what I'm going to do. The cost of this thing cost me $1,240. $1,240. I'm going to take that number there and divide it by how much I'm saving per year to figure out how many years the savings will be equal to the original cost. So $1,240 divided by how much I'm saving per year gives me 8.791. So the water heater will pay for itself in about 9 years. All right, we'll call that 8.791. We'll say, oh, about 9 years is what it will take to get this thing to pay for itself. All right, fair enough. Let's do one on your own, because I know that you're pausing the video here and doing these on your own. All right, because you're good like that. All right, so you unpause the video now, and let's take a look at it. So Gloria Lisa's old dishwasher cost her $120 per year to run. She ran it once a day. The new Energy Star dishwasher Gloria Lisa just purchased for $400 will save her 36% annually in energy costs to run it. How many years will the new dishwasher in how many years will the new dishwasher pay for itself? Okay, so we got to figure out what 36% of the savings, right? So this one's going to cost, it used to cost her $120 per year to run. So this is $120 per year to run her old dishwasher. The new dishwasher is going to be a savings of 36%. So I could express this as a decimal. 0.36 is 36% expressed as a decimal. How do I get that? That's 36 divided by 100, right? 0.36. I just moved that decimal. I just took 36%, and I essentially moved the decimal place 1, 2, right? No, 0.36. There's my decimal place. I moved it 1, 2 to get here. All right. Getting ahead of myself. There we go. So my 36% being divided by 100 gets moved over 2 because there are 2 zeros in 100. So 0.36. 0.36. Okay. And I've been using my little audio device here to do the calculations since my hands are kind of busy with other things. And, you know, I can, if you want, you tell me in the comments here whether you prefer me to break out, you know, a calculator for these. If you so choose, I will be happy to do that for you. You know, if you want to see 120 times 0.36, all right, if you like that better, 43.2, if you like that better, we can do that. And now I forgot what it said. Jeez. All right, and that's only half of what I wrote, isn't it? This was 120, right? 120. Alexa, what's 120 times 0.36?
120 times 0.36 is 43.2.
43.2. Okay, so this is how much she's going to be saving each year, all right? So over here, we found 31%. We converted it into a decimal. We times it by how much it costs to run per year, and we got this number here, right? This number here. This is our same as this kind of number over here. It's different number, obviously, but we use the same process to derive this number. Okay, and now look what we did over here. We took the how much it cost for the new thing divided by the savings, right? So this is my savings. This is my savings, so it's got to go on the bottom. For my next step of this, I'm going to take how much I saved, and that number needs to get divided by how much it cost for the new equipment. And the new equipment in this case cost her $400. So $400. Alexa, what's 400 divided by 43.2?
400 divided by 43 is 9.3023.
She didn't hear the point 2. Alexa, what's 400 divided by 43.2?
400 divided by 43.2 is 9.2593.
All right, 9.2593. All right, notice I had a little transcription error. Yeah, be careful of transcription errors. I wrote 2 here. I wrote 3 there. I had to fix that. All right, so how do we interpret the number? What we just got was the number equivalent, the same idea of what we got over here. And so it's going to take her about 9 years, 3 months, because it's 0.25. 9 years, 3 months, 9 year. All right, 9 years, 3 months to pay for itself. That's about how much it'll be. All right. Pause it if you need it. I'm going to make it all go away. And here's the algebraic stuff. Here's the algebraic stuff, which I know you all love. All right, so the old dishwasher costs R dollars to run for the year. It's replaced by, I need a space here, a new energy-efficient dishwasher that costs C dollars a year and saves P% per year in energy usage. Express algebraically the number of years it will take the dishwasher to pay for itself. Alrighty then. So let me go back. Okay, let's see. All right. What was our first step? Our first step was to take the percentage, P. So there's our P percentage, and we're going to multiply it by the savings, right? And let's see, the savings was, let's see, a new energy efficient costs C dollars a year. So the old one costs R dollars to run, all right? So, okay, R times the percentage of savings will give us a number. It will give us a number. And remember what we had to do? We had to, like, I hesitate to go back up, right? We took the amount it takes to run times the percentage of savings, which gave us a number. That number here then goes on the bottom, gets divided by the cost of the device. So let's go back over here. So what's got to happen here is this has got to go underneath the cost of the device. And where is the cost of the device? Replaced. Did I not give you the cost of the device? My bad. All right, we'll call it D, dishwasher. All right, an old dishwasher costs R dollars to run. Let me just rethink this. Make sure I got this right. An old dishwasher costs R dollars to run for a year, right? It's replaced by a new energy-efficient dishwasher that costs, C dollars a year, but saves P price. All right. I should have written this differently. You do something like this. I'll accept whatever you do. As long as you got R times P in here underneath something, we're going to be good. If it takes this form, if you use a different variable here, it doesn't matter. But that's this expressed algebraically. It's the old cost to run per year times the savings percent per year in energy usage saved, and then that's this number gets this divided by that. All right. Well, the rest of these are going to be kind of on your own. If we were in class, I would let you run with these at this point, and I can give you feedback for each one of these you put in. I can give you personalized feedback, give you hints and tips and tricks on how to do this. Go back to the examples. All the questions that follow are going to be variations and reiterations of the same stuff in these 5 examples here. And again, remember, this particular section here, section 1 of this is at least 3, if not 5 days of instruction. So it should take you, work on this for 30 minutes a day for 5 days to get through it. This is about a week worth of instruction. And then this whole unit will be a month worth of instruction because it'll be 4 sections. All right. So I hope you're all staying safe out there. Hope you're all healthy. Keep your mind active, keep your body active, keep your social life active. Make sure you're talking to people. Make sure you're calling people on the phone, video chat. Stay sane, stay healthy. See you next time. We'll get you that education you deserve.